Okay, so one thing that we didn't mention in the double slit experiment was the entanglement principle. Entanglement is a very obscure and very interesting feature of quantum systems. So imagine the following scenario. Suppose that we have two coins, and I give you one, and assume that we toss them. And when I observe my coin to see if it's head or tails, and if those two coins were entangled with each other, then I would know for certain that yours is in the same state. Right? So this is the entanglement feature. It's a very interesting feature of quantum mechanics that classical systems don't have. So when we introduced qubits in the previous video, so remember qubit was represented by the general state of a qubit. Okay, when I say qubit, we always mean the state of a qubit, so I use them interchangeably. State of a qubit can be written as alpha 0 plus beta 1. So this is the general superposition state. So this means that okay, so of course this needs to satisfy the equation modulus square alpha plus modulus square beta is equal to 1, where alpha and beta are complex numbers. So this means that when we measure psi, I will obtain the basis state 0, ket 0, with probability modulus squared alpha. Or I'll obtain the basis state 1 with probability modulus squared beta. So entanglement is a property of multiple qubit systems. Okay, we can't have any entangled system for a single qubit. A quantum system, it's a property of multiple qubit systems, 2 qubit, 4 qubits, and so on. Now consider a 2 qubit system, psi, okay, A0, 0, 0 plus A1, 0, 1 plus let me fix this, A1, 0, 1, A2, 1, 0 plus A3, 1, 1. Okay, such that sum of the modulus squares is equal to 1. So the probability to see psi in state, for example, 0, 0 is modulus squared A0. Okay, so now what if we measure the first qubit? Okay, just the first qubit. This is in fact called a partial measurement. Okay, when we attempt to measure only a part of the system, not all qubits, but only a small part of the system. So in this case, let's measure the first qubit. Okay, now what is the result of measuring just the first qubit? What are the chances of obtaining 0 and what are the chances of obtaining 1? So the probability of seeing 0 in the first qubit is simply modulus squared this amplitude and modulus squared this amplitude. So it's A0 squared plus A1 squared. Okay, so this is the probability of getting 0 in the first qubit when measured. Now, a more interesting question is the following. If we observe 0 in the first qubit, what is the new state after the measurement? Well, we know that the new state can't be 1 0 or 1 1 because these would be inconsistent with our measurements, right? So the new state will be then, we are left with 0 0 plus 0 1. Okay, but then we have to normalize the system. So the new state then becomes, so if we see 0 as the outcome in the first qubit, the new state of the system will be, let's denote this by psi prime, A0 0 0 plus A1 0 1, and then we have the normalization factor, so we're going to divide this factor to its norm, which is square root of A0 squared plus magnitude A1 squared. Okay, so let me give an example. So let's take the state psi, which is defined something in the following lines. So 1 over 2 plus I over 2, 0 0 plus 1 over 2, 0 1 plus I over 2, 1 1. So the amplitude of the basis state 1 0 is simply 0. So what's the probability of seeing ket 0 in the first qubit? Well, it's simply 1 over 2 plus 1 over 4, which is 3 over 4. And the new state will be, so this will be eliminated, right, because it's inconsistent with our measurement. The new state psi prime will be equal to 1 over 2 plus I over 2, 0 0 plus 1 over 2, 0 1, and we divide it to square root 3 over 4. Okay, so recall that taking the combination of two systems is achieved by the tensor products. So given a 2-qubit system, given 2 qubits, we apply tensor product to get a combined 2-qubit system. Okay, so this process is easy. So given any 2 systems, we just take the tensor product to take the to form the compound system. But what about the inverse process? Given a 2-qubit system, we ask if we can always factorize it into 2 systems of single qubit, so that their tensor product is the composite 2-qubit system. So the decomposition process turns out to be harder. And in fact, it's not always possible to decompose a quantum system into its smaller terms. If we can't do that, if we cannot decompose a quantum system into smaller subsystems, then that's called an entangled system. Okay, so a state that is not the tensor product of smaller states is called an entangled state. Now consider 2-qubit systems, and suppose that we have a state in the four-dimensional Hilbert space we say that Z is decomposable if Z can be written as a product of states in H2. Okay, if Z can be written as a product of states in H2. A state that is not decomposable is called entangled. Of course, this generalizes to any state of any dimension. Okay. All right, so let me give an example to a decomposable state. Now we claim that the state 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 divided by 2. So this is a decomposable state, is a decomposable state. So how so? Well, we can decompose this into two single qubit systems. So let's rewrite this state. Okay. So let's rewrite this state as 1 over 2 my screen is getting disoriented. I'm sorry about this problem. Okay. 1 over 2 0 tensor 0 plus 0 1 plus 1 0 plus 1 1, right? Okay, so and this is equal to the tensor product of 1 over square root 2 0 plus ket 1 tensor 1 over square root 2 0 plus 1. So I've just decomposed this 2-qubit system into 2 single qubit systems. So that's why this state, let's call this psi, that's why psi is decomposable. It's not entangled. So what about an entangled state? Okay, so we can claim that psi 0, 0 plus 1, 1 divided by square root 2 is entangled. Alright, so let's prove this. Now suppose the contrary that this state is entangled. So suppose the contrary, suppose the contrary, that psi is decomposable. So what does that mean? That means that we could decompose psi into two single qubit systems. So then this means 1 over square root 2, 0, 0, plus 1, 1 would be equal to, for some amplitude, say A0, 0, plus A1, 1, tensor B0, 0, plus B1, 1. Okay, so if psi was decomposable, then it would be written in this form. So let's distribute this. This is equal to A0, B0, 0, 0, plus A0, B1, 0, 1, plus A1, B0, 1, 0, plus A1, B1, 1, 1. So in order to obtain psi, then let's see what these amplitudes should be. To obtain psi, A0 times B0 must be equal to 1 over square root 2. Right? And A1, B1 must be also equal to 1 over square root 2, and the rest of the amplitudes should be equal to just 0. So we have a linear system, but this system is inconsistent, right? A0, B0, and A1, B1 are non-zero, but then A0, B0, A1, B1 must all be non-zero. So, but then neither A0, B1 nor A1, B0 can be 0. Right? So this is a contradiction. So we have an inconsistent system of linear equations. So, and by reductio, we proved that psi is an entangled state. Okay. Now observe that what happens when we measure the Bell state. This is called a Bell state. In fact, this is one of the Bell states. We will see later on that there are a few more Bell states, but this is one of the Bell states. So what happens if we measure this Bell state? Well, the probability of obtaining 0 in the first qubit is 1 over 2. But then if we measure the first qubit as 0, the probability of obtaining 0 in the second qubit is precisely 1, right? So this is where entanglement comes into play. If we measure the first qubit as 1, then we have 1, 1, right? The second qubit can't be 0. So then the probability of measuring the second qubit will be precisely 1. So Bell states will play an important role in quantum communication and in many quantum algorithms. And we will talk about this later more. So I'll see you in the next video.